Thank you, Tim, for introducing me. As you said, I'm Ross McDonald. I'm also from the MagLab, the branch of the MagLab in Los Alamos. And my title is Crowdsourcing Electrons. What you'll see in my introduction is that this is talking about how electrons behave when they don't necessarily behave as individuals, but properties that arise that are greater than the sum of the parts, that arise because of the way the electrons interact with each other. Very much like the way we might interact in a bar here this evening. So, as we said, we're here in Tallahassee. There is, in fact, another part of the MagLab at Los Alamos National Lab, which is famous or infamous for various reasons. But we also host around 200 scientists. Okay, so we also operate as a user program where we have scientists come from all over the world to do experiments, slightly different and often very complementary experiments to those that go on at the MagLab here in Florida. Okay, so as the title suggests, I'm talking about crowds. When we think about ourselves stood in a crowd, we often think about the effect of a crowd or the interactions with the other people in the crowd is to localize. Okay, so this is certainly something that can happen to electrons as well, that interactions can localize. When we think about interacting systems, you can think about how, although you might be localized, there could be some rather interesting excited states. You can think about these excited states as a single particle excited state, an electron kicked above the crowd, and this is the most simple. That was perfect timing. So while I subject you to Julie Andrews, what I'm talking about here isn't these excited states of a correlated system or of a crowd, but in fact when the crowd itself exhibits a collective behavior. And this was something that took the internet by storm probably about 4 or 5 years ago. And this is a really nice example of when humans behave in a correlated way. And that's dancing. And so what you see here is that music comes on in Antwerp Station, and I'm going to attribute this to the music and not the weeks of rehearsing that went into this. But in fact, the music causes them to correlate, and they move in such a way that they're interacting with each other, and now the state that they're in is somehow greater than the sum of the parts. It's not one crazy person dancing in the middle of a station, but it's a whole swath of people dancing. And now that's Julie in double speed. And then there's lots of people. So we'll get bored with this rather quickly. So that's my introduction. And the point of talking about, or talking to you about, and in fact the point of us spending a lot of time researching correlated electron systems, is that they lead to properties of materials that don't come about when the electrons don't interact. And the best example I've got for that is a superconductor. And to describe to you what a superconductor is, this is in fact a picture of a magnet floating above a superconductor, so it can have really exotic properties. Unfortunately, Tim wouldn't let me bring liquid nitrogen here today, so I can't levitate my small piece of superconductor on the front. But the easiest way for me to describe to you what a superconductor is to describe to you what a superconductor isn't, and in turn describe to you what electrons are. So resistance is what makes your toaster hot when you pass a current through it. That's what makes a conventional light bulb glow. So high school physics tells us how we light a light bulb. We complete a circuit, we connect wires to the top and bottom of the battery, and when we complete the circuit, we get a current or a flow of electrical charge driven by the voltage from the battery, And in this case, in the light bulb, it's dissipated because the highest resistance to that flow is happening in the filament. And that's where we're dumping the energy. That's making the light bulb hot. And it's emitting electromagnetic radiation, light in the visible spectrum, just as the toaster is emitting in infrared. Okay, so resistance is this friction to flow of electrical charge. A superconductor is a material that doesn't have that resistance. It can flow without resistance, without dissipation. So superconductivity was discovered at the turn of the last century. That's over 100 years ago. And it was discovered as the resistance of a material dropping to zero when you went to very, very low temperatures. So in this graph, this is 4 Kelvin, room temperature. This room's probably above 300 Kelvin, but is way over there. So at very low temperatures, some materials, in this case mercury, a good metal, became superconductivity. It lost this resistance. Okay, so why do we care? And one of the big reasons we care, other than the fancy picture of a superconductor's magnetic properties causing it to levitate, is that about 6% of the electricity we generate in this country is lost in the transmission process. And that's quite impressive that we have transmission lines that can work at a 6% efficiency, but that's the amount of energy required to boil something like 4 billion kilowatt hours. That's almost 2 trillion kettles of water a year, just lost through sending it from the power plants across the country. If we could do that with superconductors, we wouldn't lose that much energy. Okay, so that's the big picture motivation. The question is, if we knew enough about superconductivity that we could actually make one that works at room temperature, then we could do this, rather than superconductors that happen at a fraction of room temperature that require a lot of expensive cooling. Okay, so an interesting point to note about physics is it is very rarely a eureka moment that's revolutionary. It's often very evolutionary. And this is highlighted by the fact that it's over 60 years later from the discovery of superconductivity that there is enough experimental knowledge for theorists to sit around and decide how to explain the phenomena of superconductivity, at least this low temperature superconductivity. And in fact, for low temperature or more conventional superconductors, as I would call them, it's in fact sound waves. Very much like the music, it's the vibration of the atoms in the crystal that the electrons are moving around in that causes the electrons, in fact, to pair up, to condense into this new fluid that can flow, can carry charge without dissipation, without loss of energy. But this only works at very, very low temperatures. So one of the questions is, what sort of interactions could there be, or could we discover, that would lead to this sort of phenomena happening at much higher temperatures and at room temperature? And so, in fact, after thinking about this for many years, for a lot of my career, what actually surprises me isn't necessarily that when you have a system with many electrons in, the interactions between the electrons dominate the properties, but that there are some materials like copper, like the wiring in your house, in which there are many, many, many electrons. There's Avogadro's numbers of electrons, 10 to the 23 electrons in this. And yet the behavior of the conduction in that system is very much as if the electrons weren't interacting with each other. And so it's a rather false cartoon to say, look, when this person walks across an empty hillside, the interactions are irrelevant, whereas when you walk down a crowded high street, you have to go with the flow and you have to interact with everyone else. So something that happened, and again, this got the Nobel Prize in the 80s, very rapidly after it was discovered, was that there were certain class of materials. They turn out to be not particularly good metals. They're more similar to the ceramic of your teacup. They're bad metals, but they superconducted at rather high temperatures. And by following the sort of recipe or the chemistry, science has been able to push this superconductivity way above liquid nitrogen temperature, way above the temperature at which air, or nitrogen, 80% of air, liquefies. And so it starts to become technologically viable and significant that we could use this. So the interesting thing is that these aren't particularly good metals. It wasn't where you would necessarily go about looking for a high temperature superconductivity in advance. They're much more akin to sort of an insulator, or in fact a magnetic insulator. So that brings me to to another point that's slightly more complicated to describe. And that's the difference between not only metals and insulators, but correlated insulators. So we can think about the difference between something that's metallic and something that's insulating as how many electrons there are in there. It's a bit like playing one of those puzzles you had as a kid where you push the tiles around to try and make the picture. If there were the same number of tiles as there were spaces, you can't push any of the tiles around and you're stuck. It's localized, there's no mobility. If there's an egg missing in the box, I can roll the eggs around and move them where they want to go. If there's only one egg in the box, I can roll them around and put them where they want to go. If the box is full of eggs, I can't actually move an egg around without taking an egg out of the box. Okay, so electrons aren't quite like eggs in the sense that you can put 2 electrons in each space. And that means that not only is there this condition that when it's completely empty, there's no eggs to move around, or when it's completely full, there's no eggs to move around, but when you've got it exactly half full, if there's some energy penalty, there's some reason why you can't put 2 eggs in the same slot, it might also not want to move around. And so electrons, we know from rubbing a balloon on our clothes and sticking it to the ceiling, electrons want to attract when you have opposite charges, but when they have the same charge, they want to repel. So if there's an energy penalty for putting 2 electrons of the same charge in one box, then there's a reason then for when you've got half a box full of electrons or half a box full of eggs that these things are going to want to localize, they're going to want to stay static, and they're doing that because they're interacting with their neighbors. And so that's something that that Mott came up with. In fact, we call this a Mott insulator. This is different, and it's very subtly different, and I'm hoping that I've described this in a way that you're not going, huh? What's the difference between 2 electrons and an egg? But that's what we would call a correlated insulator. That's a material where the correlations are strong and are dictating the properties. Okay, so what about the magnetic properties? So you're here because you know something about the MagLab. And so you know already that I'm not, when I'm talking about magnets and magnetism, I'm not just talking about Wiley Coates' Acme magnet, and that electricity and magnetism are in fact very intimately intertwined. And I think this is appropriate because I'm from New Mexico. So this is the picture we often draw, or school textbooks draw, of a bar magnet having a north and south pole, and we draw magnetic field lines as lines that eat their own tails going through the bar magnet and looping around in circles. And when we put 2 norths together, they repel, and norths and souths attract because the way the arrows can flow. So that's a nice visual picture for what a magnet is. A coil of wire, or a current, more importantly, flowing through a coil of wire, creates a magnetic field that's very much like a bar magnet, like this little dipole magnetic field. And this was something attributed to Ampere, that he basically discovered that electricity or electrical charge moving produces magnetism. Similarly, and this is where I'm going to attempt to do a demo, and you guys, I'll pass something around to you once I've done it. And that's that Michael Faraday demonstrated that a moving, or in fact a changing magnetic field can induce currents and can induce magnetism in nearby materials. So for this, I need an assistant from the crowd. Arkady. You didn't know I was going to do that. Okay, so Arkady's got here is a plastic tube. It looks a little bit fatter than my bit of copper plumbing from home, but essentially they're the same thing. I'm also going to give him a rather strong piece of magnet. Don't demagnetize yourself. Okay. Okay. So what we're going to do on the count of 3, we're both going to drop the magnet through the tube. As you can see, they're about the same length. And if you hold it up like this, you can see about the same diameter. And I hope the magnets fit inside. So, you ready? On your marks, get set, go. Oh, what? Okay. Never work with children, animals, or Russians. Okay, you can rejoin the audience now, thank you. A round of applause for my... Okay, so the point of that demonstration was meant to be, and things never go right. Let me see if my magnet fits through the tube. Maybe. No, it doesn't work. Okay. I think my magnets have got hot and expanded in. Okay. So the idea of that demonstration was that if I drop the magnet in free space, you can see how quickly it falls. If I drop the magnet through the tube, there's a couple of things. One is I'm going to hold it close to the microphone, and I want you to listen, because if it hits the tube, you'll hear this as it rattles down the inside. You hear anything?
No.
So the only reason for the slits is so that you can see it fall. Wait a minute. So you guys can do this at home. This is a bit of copper plumbing that you can get at Home Depot for your house. This is a magnet. It's a pretty strong magnet, but it's not that much stronger than a refrigerator magnet. And what this is telling me is that copper isn't a magnetic material. The magnet doesn't stick to copper. I can't pick it up. If I was to drop it through the tube that's made of plastic or an insulator, it would have just fallen just like it did through free space. So this is a property of electromagnetism that I didn't experience as a kid, that I didn't realize. I was used to sticking magnets to a fridge and knowing that they repel or they attract. This is something where the moving magnet or the changing magnetic field is inducing currents that's making the opposite magnet. So I'm going to pass this around and you guys can play with it. Look down the tube, watch it. It's going to float down the middle. It's kind of cool. Watch the magnet doesn't stick to anything. Or wipe your credit cards. Here's my skeptic. There's a bit of feedback. It's all yours. I probably wouldn't put that on your phone, by the way, or your credit card.
The colder the tube, the slower it goes.
Indeed. So if I was allowed my liquid nitrogen, I could dip it in the liquid nitrogen. It takes about 30 seconds after I've got the tube nice and cold. Ha ha ha. Okay. Okay. So there's one more. Okay. So if the magnet doesn't move, there's no attraction. If the material's not a conductor, there's no attraction, as Arkady so beautifully demonstrated. Okay, so there's one more quirk of electromagnetism that turns out to be very useful, and that is there's this rather peculiar or particular geometrical relationship between the direction of the magnetic field, the motion of the charge of the electrons, and the force exhibited on them. And this is the Lorentz Force, and this is the fact that the force is both perpendicular to the direction of the current and the direction of the magnetic field lines. So I've got another little demonstration for this. And this is again something you can do at home. I need three things. That's a bit bent. I've got a piece of copper wire that I've bent into an M shape for the MagLab that I've ripped out of my house at home. I've got a 1.5 volt C-cell battery, nothing special about that, and I've got a couple of, and I have a couple of these magnets. The interesting thing about these magnets is they also are metallic as well as magnetic, and that will be important. So I'm going to stick the magnets to the end of the battery, stand it on the table, and I'm going to take my little wire M. It turns out the wire M is going to complete the circuit. And what you see is that I've made a motor, if it was to balance. There you go. So it will spin round. And you can imagine there's several things we can do to test this. We could reverse the direction of the magnets. And then, if this was a high school class, I would ask for a poll as to what would happen, and it's going to spin the other way. Wait a minute, there you go. So I'm going to pass this around as well, and you can play with it. You can also reverse the direction of the battery. It's just harder to balance the thing on top.
That's where the
It's
art.
more likely to stay then.
Maybe it's more likely to stay. So have a play with that, and I'll explain what that shows us. Pass it around. Okay, so this is my cartoon picture of this. There's the M, there's the battery, there's the magnet. As I said, the magnet, as well as providing the magnetic field lines, also is metallic, and so it completes the circuit. So the arrows show where the current is flowing. The magnetic field lines that loop from one end of the battery to the other happen to cross the current direction, and they're perpendicular here. And so this is why I've drawn a hand, is that when I have two things that are perpendicular, and I'm going to draw it on this side, my finger is going to be the current, this is the field line. I have a force on this wire, or these charge carriers out, and when I reverse this over here, I have a force that's in. And this is this peculiar vector relationship that enables us to make motors and most of the things that we use to both generate electricity and to provide motion. Okay, so all of this can be summarized in some rather hideous-looking differential equations that can be written surprisingly simply with a lot of characters. But the important thing to take away from this slide is just that everything we experience is something to do with electromagnetism, whether it's light, whether it's what we touch. Okay. So because I haven't got my liquid nitrogen, I'm going to skip these slides because I'm already waffling on much longer. But as I showed you at the beginning, the magnetic properties as well as the conducting properties of superconductors enable us to basically make them like a perfect image to the magnet. You know, if you take two magnets and you try and float one on the other, it's unstable. It always wants to flip over. You'd have to be able to spin that top magnet. That's essentially what you're doing with a superconductor. That's what would enable levitating trains. Okay, so magnets survive in superconductors, if they're cold enough, keep their superconductivity in moderate magnetic fields. But if we want to study something, we often want to be able to break it or to tweak it or to change it enough. And so to destroy the superconductivity, one thing we need is a rather strong magnetic field. So to put that strength into context, here's the Earth's magnetic field, much, much weaker, although much larger volume than a refrigerator magnet that you're playing with. Certainly much weaker than the strength of a junkyard magnet. But the sort of research magnets that they use at the MagLab here in Florida, that I use in Los Alamos, are much, much stronger than that. You can see, you know, thousands, almost 1 million times stronger. And so the interesting thing to note is that these big magnets, because of resistance, because of the reason light bulbs glow, as well as creating a magnetic field, create heat. And so the world's most powerful DC magnet, meaning a magnet that you can turn on with a direct current, that's what DC stands for, and leave on as long as you can keep the thing cold, is here in Tallahassee. And this is taking 30 megawatts of power. This is generating a huge amount of heat, and very much what's limiting this is how much of that heat can you pull out of the system. Our solution to that in Los Alamos is that we can go to higher magnetic fields if we do it for a short period of time. And by a short period of time, I mean that we pulse the magnet for a fraction of a second. That generates a lot of heat. We might wait an hour or so for the thing to cool down, and then we can do it again. The challenge now is, how do I measure my piece of superconductor, my sample, in a short period of time? The way we would generate a pulse magnet is very similar. We have a coil of wire, now with a lot of reinforcing material, but it's a coil of wire. And just like when we wanted to light the light bulb, we complete the circuit to some sort of voltage source. In this case, it's a capacitor bank. That's a bit like a battery. It stores electrical charge. When we close it, the current flows and it produces a magnetic field. Now, the challenge with us producing higher and higher magnetic fields like this is that the forces on the magnet itself, on the coils, become very, very large. In fact, if you think about that force as a pressure, a force per unit area on the reinforcing material that's holding these coils together, the pressure is something like 30 times the pressure that was on James Cameron's submarine when he went to the bottom of the Marianas Trench a couple of years ago. So we're really approaching the yield strength of all known materials in order to hold these magnets together. That's what limits how strong a magnet we can make. And in fact, these magnets have huge forces on them, both wanting to rip them apart. This is a magnet this is about life size, actually. It's about that size. This would produce, this says this was 80 Tesla. This sort of size magnet typically produces somewhere between 65 and 80 Tesla. And when they fail, when they eventually break, and all pulse magnets break, they fail pretty catastrophically. That's a smaller magnet that's only using just over half a megajoule of energy. To put this into context, a megajoule of energy is what we get eating a Snickers bar. So humans, we're pretty energetic things. We burn a lot of energy, but we burn it relatively slowly. So for me to burn a megajoule, if I'm carrying a heavy backpack and I hike up one of the mountains in New Mexico, it takes me about an hour to climb 1,000 meters. If I'm going really hard, that's me gaining a megajoule of potential energy. So I can't burn that very quickly. If I want to pulse the magnet in a couple of milliseconds, I need a way of releasing that energy more quickly, and that's why we use a capacitor bank. It's not a very efficient way of storing the energy. A capacitor bank to store a megajoule or a couple of megajoules is about the size of this half of the bar. But I can release it in a fraction of a second, most of the time without it destroying the magnet. And this is a box full of rubble when one of these magnets eventually fails. Okay, so the higher the magnetic field we want to produce, the more reinforcing material we have to put in to hold the magnet together. And this is a couple of photos we took as a joke a couple of years ago. This is our 100 Tesla magnet that set the world record for a non-destructive magnet pulse in 2012. We use this as a research tool on a weekly basis. And this was just a joke because I thought it was funny to stick a refrigerator to a magnet rather than the magnet to a refrigerator. It's photoshopped. The magnet's not switched on, or I wouldn't be stood next to it drinking milk. But the point is, this now has over 100 megajoules of energy stored in the magnetic field. The system to deliver it is delivering over 200 megajoules of energy. Because we would need a capacitor bank something like 50 times the size of this room to do that, we now use a motor generator. We basically store the energy mechanically. We've got this thing, so to put the size into context, this is a very pretty sort of blue lit photo, but this is my wife stood in front of it. This thing's like 50 tons of rotating mass at 1600 RPM. So when we basically put the brakes on by connecting this to the magnet and a current flows. And this is where I've got a sound effect that you may have heard earlier. Here we go. What's happened to my mouse? Sounds like Godzilla, huh?
Like Pink Floyd.
It's a bit of Pink Floyd. They could sample it. I don't think we'd charge any royalties for that one. So the reason it's making that noise is, in fact, it's an AC generator. It would be used normally in a coal power plant or a nuclear power plant where you'd have a steam turbine on the end. You'd use the heat from the power plant to create steam that would turn the generator, and then you would get a voltage out the end, very much like you'd use hydroelectric power in the Hoover Dam. It's designed to generate AC power, meaning an alternating current like you get it out of your plug socket at home, and we're basically rectifying that. We're turning it into this waveform. But there's still a little bit of ripple on this. And this ripple happens to be around 600 hertz. And that's the sound that you're hearing, is the fact that the conductor in the magnet and the conductor taking the current to the magnet is actually vibrating and oscillating because of the forces between them. It's acting like a speaker. The reason when you hear it, it changes note is because as we take the energy out of the shaft slows down a little bit and then it comes back up. And so the pitch of the sound you hear goes, I think it sounds a bit like a rip saw going through a bit of plywood. That you have that kind of like, the saw slows down as you make your cut. Okay, so there's another picture, or another, here we go. So this is a video looking down on top of the magnet. This is a human scale, so this is a railing for someone. And if you look up here, there's a chain hanging from the roof of the cage that the magnet's in. And that's about 10 feet away from the magnet. You can see getting pulled across the room. Now the field strength out there is a small fraction of the field strength in the middle of this coil where we're putting our sample. Probably about 1,000th is all that's needed to pull this chain. Okay, so this is this thing. This is a human size set of coils with lots of reinforcing material, the electrical connection to this big generator, and we use it to measure the properties of these superconductors, of these other correlated electron systems. This is what we call a probe. It's basically a stick that we put our samples on. The samples are often so small that we can't see them with the naked eye. This stick is in fact 1/4 of an inch diameter, and we're sticking it in this magnet that's bigger than me with a power source that's bigger than this building. And that's so that we can subject these materials to really, really high magnetic fields and try and measure their properties. Measure how their magnetism changes, measure how their resistivity changes, measure how their length changes. Various fundamental properties that can help us understand how the material behaves, how the electrons interact. Okay, so back to interactions. The question is, how do we use these high magnetic fields to measure these interaction effects? And to try and get you to understand how we think about this, I'm going to go all the way back to some sort of high school physics of Newton's laws, the classical mechanics. So Newton came up with, or basically defined the concept of force and mass to be able to describe equations of motion, how something moves in our world of classical mechanics. And this basically describes this, I guess it's Newton's second law? I hope I'm getting that. Yeah, it's second law. Thank you for the encouraging nods from the audience there. So Newton's second law relates force to acceleration, meaning when I apply a force to something, it starts to accelerate via the mass of the object. And the cartoon here basically says that you can apply the same force with a golf club to a golf ball as you would apply to a van, just you're going to get a lot more acceleration out of the golf ball because the mass is small, and hardly any acceleration out of the van because the mass is large. So that's how we think about mass and the equations of motion for classical objects. For correlated systems, I think about it a lot more like the way honey behaves or the way molasses behaves. Imagine you take your finger and you drag it through the honey. You're trying to push honey across the jar. The way that you accelerate that honey doesn't now depend on just how heavy the honey is that's on the end of your finger. It depends on the flow of all the other honey in the jar around it. And so we think about now with our electron systems that the electron, we describe it now when it's in this crowd, it's almost like the crowd itself has a mass. If I want to push any one person across the bar, I've got to push everyone else out the way. They're interacting. And so this concept of effective mass comes by measuring how the electrons move and behave and can reveal how the electrons are interacting. There you go. It's a way of describing how we accelerate something. Okay, so that's classical mechanics. Quantum mechanics basically says that the materials, when they're on a very small scale, behave as both a particle and a wave. They have properties of both. So when you look at this picture, what do you see? If we polled the room, probably half the people would see the wave, half the people would see the particle. I would argue that probably shortly after the picture was taken, they were indistinguishable as both particle and wave. The important thing about quantum mechanics is neither description is correct, but you have to have some of the description of a wave and some of the description of a particle. In fact, a description involving both works best and describes most properties. So where do we experience that? When we go out in the parking lot in the rain and we see puddles with oil on them, we see a rainbow. Why do we see a rainbow? That's because the light that's falling on the puddle is in fact a wave, and that wave, as it passes through the oil, which has a different refractive index, interferes with itself. And we know what it's like when you make waves in the bath, you throw rocks in a pond, you can get constructive and destructive interference of waves. They add together or they cancel each other. And so that phenomena leads to different colors being reflected. Different colors, in fact, have different wavelengths. Electrons behave in a similar way. They also have a wavelength as well as a particle-like description. And so if we go back to this cartoon, this picture of when a charged particle, an electron, is moving in a magnetic field, it experiences a force that's both, so if this is the field and this is the velocity, it experiences a force that's both perpendicular to the magnetic field and its velocity. What does that make it do? It makes it want to walk around in a circle. And when something's walking around in a circle and it's a quantum mechanical object that has a wave function, it's going to see its own wave function. And that means that it's going to interfere with itself constructively or destructively, depending how big that circle is. Turns out that the circle depends on how strong the magnetic field is. You can imagine the stronger I make this magnetic field, the bigger the force, the tighter the circle. Okay? This graph that you kind of can't see very well, but maybe in the next slide you can, is the resistance of a superconductor. So over here, low temperature and low magnetic fields, there's no resistance. Electricity flows without dissipation. We put on a big enough magnetic field and we regain the resistance of the material. There's now dissipation. But very interestingly, as we ramp up the magnetic field, this dissipation oscillates. And the way this dissipation oscillates tells us about the motion of this electron in the material. It tells us about the effective mass of the electron, which in turn is telling us about the way it's interacting with all its fellow electrons, which is what we believe gives rise to the superconductivity. Okay? And to be in to keep the style of giving credence to or or citing physicists of old. This is the postdoc who's now going on to better things, Brad Ramshaw, that did these really nice measurements on some high temperature superconductors in our highest magnetic fields. These are superconductors where, so again, remember I said that at 77 Kelvin, the air, nitrogen liquefies, and 80% of the room would liquefy at this temperature. These are superconductors that superconduct above the temperature at which we would liquefy air. What's interesting about these materials, these are the materials that, if I show you, here's a piece of one. It doesn't look like the copper that I had. It's not a shiny piece of metal. It looks like a hard ceramic. I'll leave it up here. I won't pass it around because it's a little bit brittle. If you drop it, it will probably shatter. Because it's a ceramic, it's more closely related to an insulator. So again, if I go back to my cartoon picture of a box of eggs, if I now start taking the eggs out of the box, if it's completely full of eggs, I'm over here on this, I'm calling it hole doping. I'm taking eggs out of the box. I'm leaving holes in the box. As I start to do so, I suddenly have this degree of freedom where I can shuffle the eggs around. I might still have the strong correlations that they don't want to be doubly occupied, but I've now got an ability to move them around. In this region of parameter space, I have really strong superconductivity, this high temperature, not quite room temperature, but high temperature superconductivity. And what we find is, if we make a whole series of samples and we measure these oscillations that tell us about this effective mass gets stronger and stronger, or heavier and heavier, as we get to where superconductivity is strongest. And that's telling us that we're somehow probing the most relevant interactions for why this thing is superconducting. It doesn't tell us yet how to make a superconductor, gives us some guiding principles as to where to look, but we do have a better understanding of these interactions that give rise to superconductivity. Okay, so this is sort of the end of the correlated part, perhaps, of the talk. So hopefully I haven't completely lost everyone and going full circle from how we behave in a crowd to why we have big magnets and superconductors. But I thought it was worth showing some of the challenges with making even higher magnetic fields just at the end for some. You can see why we do this in Los Alamos. So, as I said to you, the world record for a pulsed magnetic field, if you don't want it to be destructive, is 100 Tesla. And we have to have this huge magnet system to be able to distribute these forces, these magnetic pressures. If you want to go higher, you basically have to live with the fact that the magnet's going to destroy itself. One thing you can do, and this is why I call it Wile E. Coyote Strikes Back, is here's Wile E. Coyote with his explosives, is that you can use shaped explosive charge to provide a force in the opposite direction from the magnetic force. And in fact, you can compress the conductor of the magnet faster than the field can leave the magnet, and you can generate very high magnetic fields. The problem with this is a human scale now. This is a staircase. That's your one shot at doing an experiment, and science tends not to work like that. As I said at the beginning, it's not your eureka moment of, hey, we've done this, we can go home. It's years and years of repeating, of testing, of trying to work out what's going on. So this tends to be not a particularly practical way of generating high magnetic fields. Oh, don't need to see a video of people blowing things up. Another way of doing this is basically to pulse the magnet fast enough that the inertia, the mass of the copper that makes up the magnet, holds together whilst the pulse is taking. The problem is now you have to make your pulse not milliseconds duration, but microseconds in duration, a millionth of a second. The coil itself now, instead of being many, many turns of copper, is this single loop, and you can see here it's next to a nickel or a dime. This is a centimeter diameter. And we pass a huge current through this. We pass about 2 million amps through this loop of copper. We're only using a fraction of the energy because now we're delivering that current in a much shorter period of time. So this is only about 1/4 of a megajoule, less than that actually. And what you see is a lot of sparks and an explosion, and the magnet's destroyed itself. The important thing is the magnet destroys itself radially symmetrically like this. So your experiment that sat in the middle survives. So I can put my interesting material in the middle of this, and boom, the thing explodes in a fraction of a second. And if I'm clever enough and I can do a smart enough experiment, I can measure something to do with my sample. So I thought I would end with, and maybe this will work. Where's my mouse gone? All right, let's see. Don't look at the screen. I apologize for the music. So this is the charge voltage. And my boss put the music to this, so, but that's the ensuing fireball, essentially. So the point here is that we're generating much, much higher magnetic fields. The question for the future is, how do we make this useful? How do we probe the next generation of materials properties that require bigger and bigger magnetic fields when we only have a few microseconds to do it in, when we have this harsh environment that's a plasma somewhere around my sample that I want to keep close to absolutely 0 Kelvin. So thank you very much for listening. I hope I didn't lose you all completely. Ask lots of questions, come play with stuff. I hope at least I entertained. I don't know.
My understanding is that out in the west coast, Washington or Oregon or somewhere, there is a magnetic lab that's substantially stronger than the one here. Is that correct?
Yeah, so it's New Mexico. So okay, so the question was, and maybe you missed a little bit at the beginning of the talk, and that was that his understanding is that there's another magnet lab with stronger magnetic fields somewhere out west. And my answer was yes. It's actually part of the same magnet lab.
The second thing is, are the capability different than what you have here?
Okay, so that's actually a great question. Why, in fact, we're one magnet lab, although we're at different sites, in the sense that we're all, we have a common funding from the National Science Foundation to do high field research. They're obviously very complementary techniques. We measure a lot of the same materials, but there are limitations to what you can measure. So for example, if you've got an experiment that's looking at the way, say, light interacts with your superconductor, you might need a certain period of time to capture enough of the light coming from that superconductor that means that you need to turn the magnet on for minutes at a time. Your signal to noise might be such that you really need to average for a long period of time. There might be some other sort of measurement where, let's say you want to look at how the heat capacity of the sample responds, how when you put in a heat pulse, how much temperature does it change? That's again something that can tell you fundamental things about the interactions in a material. That takes a finite amount of time. So I would say that the reason the two magnet labs, or the two parts of the magnet lab, are so complementary is there are things that you can only do at the highest magnetic fields, and there are things that you can't do in a pulse field environment, or are very, very challenging to do on a millisecond timescale. So that's very much why we have these multiple approaches. Cool. Was there?
How do you go about eliminating obviously bad choices like superconducting?
Whoa. Time. So, yes, it's time. So that's time. So I think at some level I would say not the dirty truth, but the honest part of this is that very much the discoveries that have been made, despite the great theoretical advances, have come about because of luck. It's kind of like cook and look. If you mix this chemistry, you mix this and this and this, you make this material, and if you explore its properties, something interesting happens. We've moved from there to the point where we have very good overarching and guiding principles as to where things might be interesting. For example, we now know that if you take one of these materials that's close to this half-full system that shows strong interactions and you perturb it in some way, maybe you squeeze on it, maybe you change the chemistry so that you've got a little bit more, or a few more electrons, few less, then you find these sort of emergent states pop out. But that's sort of one of the challenges of something that is, by definition, an emergent phenomenon, something that pops out of the unexpected, is a priori you don't necessarily know what you're looking for. And at the end of the day, when you're looking for funding for research, it's very nice to be able to say, oh, we've got this great idea, we're going to design this and we're going to make this. But a lot of research really is asking difficult and fundamental questions about why does something that you don't think has got any relevance to society, like this magnetic insulator, why does it behave the way it is? Why is that such a challenging problem to describe theoretically? You can no longer write down an equation of motion that's trivial when it's an equation of motion for the 10 to the 23 electrons. That's a really tough problem. And it's only sexy in some way because it leads to these emergent properties. Maybe we'll get better at this, but right now, that's sort of where we are. There's a lot of looking, there's a lot of, hey, this is interesting, this is kind of related, maybe that's interesting as well. Guiding principles.
Well, it seems promising because the best thing about being a male scientist is you get to blow stuff up.
That's all I do. I'm not sure that's limited to men, but I think it's a childlike character that maybe. Yes.
Are yttrium-based materials still the most promising?
It's so I would. So the question was, are yttrium-based materials the most promising for high-temperature superconductor? I would take a step back from that and say, at least at the moment, the highest superconducting transition temperature of a material at sort of ambient pressure conditions, but at low temperature, are materials that have, the common thing is that they have copper oxide in them. So the copper sits and when it's surrounded by oxygen, so like, like copper soot, like if you've smoked some electronics at home, it's sort of black copper oxide. When the copper's surrounded by oxygen rather than sat in its metallic state, it's insulating, and it looks like it has one electron basically sat on each copper atom. So it's very close to this, one electron per site per copper. As we now tweak that, and we tweak it by putting it with yttrium, with mercury, with other materials, we push it away from being this magnetic insulator, and that's where we find the high temperature superconductivity. I wouldn't say it's limited to that. There are other systems with iron, where it's the spin on iron that gives rise to superconductivity, that has perhaps more technologically relevant properties, such as it being a more ductile rather than more of a ceramic material. But at the moment, not a highest temperature superconductor. So to say which material is more promising, I don't know. Time for more beer. Thank you.